In this lesson, we'll be talking about what the GMAT considers to be one of the more advanced content areas on the quantitative reasoning section, especially for word problems, and that is probability. So let's first just define how probability works, and the easiest way to do that is as a fraction, where the probability, or P, is going to be equal to your desired outcomes as the numerator, over the total possible outcomes as your denominator. So probability is always going to have a set range in that we know the least possible probability is 0 and the greatest possible probability of any single event is 1, inclusive, because a probability of 0 means it's impossible. So there are no desired outcomes. And if I have a 0 numerator, no matter what the denominator is, I know that the fraction itself is going to result in 0. So if you have something that is impossible, that has a probability of 0. Now, if you have a definitive certainty, meaning all desired outcomes are all the possible outcomes, then you're dividing the possible by itself, which gives us 1, and that's your maximum value for any probability. And you can even think of this as percentages, because we know that if something has a 0% chance of occurring, that means that it's impossible. If it has a 100% chance of occurring, that means it is definitively certain. And there is your inclusive range of all probabilities from 0 to 1 based on the fraction structure of probability as a single event. So how do we deal with multiple independent events? Well, what we have to do is we find the probability, the desired out of the possible for the first event. Then we multiply by the desired out of the possible for the second event, and that's going to be the probability that both events independently occur. So let's take a look at an example. What is the probability of rolling a 1 and then a 2 in that order using a single 6-sided dice? So you can see kind of the structure of the dice, but we're just picking one of them that you see on the screen here for this example. So the number of desired outcomes for each event is going to be 1. Whether I roll a 1 or a 2, there's only one side of the 6-sided dice that is going to have that on its face. So we've got a 1 out of 6 for rolling a 1, and then a 1 out of 6 for then rolling a 2. So we need each of those things to happen for both to happen. So you have 1 out of 6 times 1 out of 6 is equal to 1 out of 36, and that is the probability of rolling exactly a 1 and then a 2 in that order if you have a single 6-sided dice and roll it twice. Then we've got to consider what would happen if we want to count the number of accepted outcomes for a single event. So when you have the probability of one thing that is desired, plus the probability of another thing that can happen on that same event and it also is desired, that is going to be the probability of either. So another example, what is the probability of rolling a 1 or a 2? Well, the number of desired outcomes here is 2 because we could accept a 1 as the roll or a 2 as the roll. So there are 2 possible desired outcomes. And the probability for either occurring is going to be the 1 out of 6 probability that it's a 1, the 1 out of 6 probability that it's a 2 added together to get to 2 out of 6. And that, of course, can be reduced down by dividing by 1 as a fraction of 2 over 2, and that gets to 1/3. So the probability of rolling a 1 or a 2 is going to be 1/6 plus 1/6, whereas when we wanted to roll a 1 and a 2, it was 1/6 times 1/6. Now, there are certainly more complex events that can be tested on the exam. So let's take a look at one more example. What is the probability of rolling at least 1 3 in 2 rolls of a single 6-sided dice? So the number of possible iterations of the desired outcome is 3, because we know you can get a 3 on the first roll, or a 3 on the second roll, or 3 on each of the 2 rolls. So the probability of rolling a 3 on the first roll, well, we want a 1 out of 6 chance of the 3 being the face that's up, and that's all equal. And it doesn't matter what happens on the second, because what happens on the first is all that matters in this first iteration. So that's going to be 1 out of 6 times 6 out of 6, because everything that is possible is desired, provided you rolled a 3 on the first roll. So you got a 6 out of 36 chance that you roll a 3 on the first roll, irregardless of what happens on the second. Now, rolling a 3 on the second roll is basically the same thing, just reversed. So we don't care what the first roll is. But on the second roll, the desire is to get a single 3 out of the 6 possible outcomes. So 6 out of 6 times 1 out of 6 for the single desired outcome on the second roll is going to be another 6 out of 36. But we have to also consider what happens when we roll a 3 on both of the two independent rolls. And that would be a 1 out of 6 being the desired first 3, times 1 out of 6, the desired second 3, which is another 1 out of 36 chance that you get exactly 2 threes. And you must avoid double counting by using the group equation for overlapping sets to make sure that you didn't count the both rolls in as a unique outcome for both the first roll and the second roll. So that's going to be our total is going to be equal to group 1 plus group 2 minus the overlap plus neither is going to basically incorporate all of the aspects of a Venn diagram. So in this case, we know that the total of all probabilities is 1. So the probability of at least 1 3, because the total is just that 1, is going to be equal to the 6 out of 6, or sorry, 6 out of 36. That was our first roll being a 3 plus the 6 out of 36 that would be the second roll being a 3, minus the 1 double count of a 3 on each of the two rolls, which gives us 11 out of 36 as the probability of rolling at least 1 3 in the two rolls. Now, we can also simplify this a little bit by using our at least structure. So we know that an at least probability is going to be equal to 1 minus the exception or exceptions probability. So we could use the same example ultimately. And we know that the probability of rolling at least 1 3 in two rolls could be solved by determining that the number of desired outcomes is going to be 1 for each event. And the number of exception outcomes is going to be 5 for each event because you've got 5 not a 3 sides. So our exceptions probability would be the 5 not 3 sides. And then the 5 not 3 sides again for the second roll. So we take the exceptions of not a 3 being 5 out of 6 on the first roll and not a 3 being 5 out of 6 on the second roll. And that would be 25 out of 36 instances where there are no 3s in the two rolls. So then we just take that at least structure and we'd subtract those 25, out of 36 not 3 rolls and subtract them from the total of 1 or 36 out of 36 and know that there will be 11 out of 36 ways to have at least 1 3 because there are 25 out of 36 ways that there are no 3s in either of the two rolls. So these are basically the 3 structures that you'll really encounter. We know that with at least you want to take 1 minus the exceptions. If you're trying to find the probability of this or that, you're going to add the two independent or the two probabilities for that single event. And if you're looking at a probability of this and that, you're going to multiply the two probabilities together to determine that ultimate probability of both of independent events occurring. So let's head on over to the whiteboard and take a look at how one of these problems can be solved using your scratch work as you engage with the GMAT focus. Here we have a sample problem solving question. We're going to set up our scratch work as we do every time. We've got A through E with a little line over top for what the question is asking. You can decide on your own whether you want to write out these short little expressions, the decimal and exponent articulations of the numbers. If it's earlier in the section, I might consider doing so. For the purposes of this example, we won't. It's kind of a 50-50 thing in this case. But we do note that our answer choices are in decimal form, so that will help us to decide how we want to engage with our non-integer values for managing the problem's math. So we skip to the end. If there is a 4% probability of an individual fuse failing during any 24-hour period, then the probability of the building's power being shut off during any given 24-hour period is closest to. So we're being asked for the probability of a shutoff. So we go to the beginning and we read in a utility room fuse box. There are 5 fuses. So fuses is equal to 5. If one or more of the fuses were to fail during any given 24-hour period, then power would be temporarily shut off to the entire building as a safety precaution. So we know that if any of the 5 fail, then we get a shutoff. And we learn if there's a 4% probability of an individual fuse failing, so 4% is our fuse fail probability. That means that there's a 96% fuse not fail probability because those are the only two options. So now, rather than just going headlong into considering all of the different ways that a shutoff is possible, you might note that there's only one way that a shutoff doesn't occur, and that's ultimately going to be our exception. So our exception is going to be that all five don't fail. So we then can basically use our at least structure, knowing that the shutoff in this case is going to occur any of the outcomes except for the one situation when all five don't fail. So, what we want to do is consider how they're not going to fail. So, we know that our don't fail probability is going to require basically 0.96 for the first fuse, 0.96 for the second fuse, 0.96 for the third fuse, 0.96 for the fourth fuse, and 0.96 for the fifth fuse. And that means it's 0.96 to the fifth power is going to be that there is no shutoff because none of them failed. But of course, we don't want the probability of no shutoff. We want the probability of there being a shutoff. And that would be our exception. So there being a shutoff is going to be equal to 1 minus that 0.96 to the fifth. And we can see that matches choice E and is our correct answer. And you can see how with probability, much like some of the other higher end difficulty word problems that you'll encounter on the GMAT focus, it's more about just understanding logically what the problem is telling you and then working through that conceptually as opposed to actually figuring out what 0.96 to the fifth is, for example. So go ahead and practice some of your own probability questions to improve at this aspect of word problems on the quantitative reasoning section of the GMAT focus exam.